You have probably held a glass cup up to the light and noticed how clean and rigid it feels, even though you also know, in some vague way, that glass comes from sand. A common assumption is that sand is loose and granular, so anything made from it should be either crumbly or easy to melt again. That assumption is understandable, but it leaves out the main reason glass behaves the way it does. Why does a pile of sand become a single solid sheet or bottle? What exactly changes inside the material when it turns into glass? And why does glass sometimes seem like a solid, yet also gets described as something like a frozen liquid? In the next few minutes, this will be explained carefully, in plain language, without shortcuts. The first misconception to correct is the idea that glass is just sand that has been pressed together. It is not compressed sand. Sand is mostly made of silica, which means silicon and oxygen atoms bonded in a repeating structure. In many natural sands, those atoms are arranged in tiny crystals, and the grains stay separate because they are individual particles with air gaps between them. To make glass, the silica is heated to a very high temperature until the bonds can rearrange and the material becomes a liquid. Then it is cooled, but cooled in a way that prevents the atoms from snapping back into a neat crystal pattern. That last point is the key. Many solids, like salt or quartz, are crystalline. Their atoms line up in repeating patterns, like bricks in a wall. Glass is different because it is amorphous, meaning without a regular shape. Its atoms are locked in place in a disordered arrangement, more like a liquid's internal structure, but without the ability to flow. When molten silica cools quickly enough, the atoms lose mobility before they can organize into crystals. The result is a rigid, solid material with a disordered internal structure. To understand why this produces something hard and solid, it helps to separate two ideas: ordered versus locked. You can have a solid that is ordered, like a crystal, and you can have a solid that is disordered, like glass. What makes something solid is not the neatness of the pattern, but the fact that the atoms cannot move past each other easily. In glass, the silicon and oxygen atoms form a connected network, a kind of three-dimensional web. Even though the web is irregular, it is still strongly bonded, so the material resists deformation. That is why glass can be transparent and strong, even though its atoms are not arranged like a crystal. In real manufacturing, pure silica is difficult to melt because its melting point is extremely high. So glassmakers usually add other materials, like sodium carbonate and limestone, which lower the melting temperature and make the molten mixture easier to shape. These additions also change properties, like hardness, chemical resistance, and how easily glass cracks. So while glass is made from sand is basically true, it is often more accurate to say that most common glass is based on silica from sand, modified with additives that make it practical. There is also a persistent claim that glass is still flowing, and that old window panes are thicker at the bottom because the glass slowly sagged over centuries. In ordinary conditions, glass does not flow in any meaningful way on human timescales. The thickness differences in old windows are mostly due to older manufacturing methods that produced uneven sheets, and builders typically installed the thicker edge at the bottom for stability. Glass can flow at very high temperatures, and it can slowly relax under extreme conditions. But at room temperature, it behaves as a solid for all practical purposes. In everyday life, This matters because it explains why glass can be shaped like a liquid during production, then remain rigid for decades. It also explains why glass breaks the way it does. Because it lacks a crystalline structure, cracks can travel through it in a relatively smooth path, which is why broken glass can form sharp edges. Tempered glass and laminated glass are designed to manage this by changing internal stress patterns or holding fragments together. So the main idea is simple. Sand provides silica, heat turns it into a liquid, and cooling locks the atoms into a solid network without crystallizing. Understanding this helps make sense of why glass can be both transparent and rigid, why it can be molded, and why its breakage can be engineered for safety. If there are other everyday materials that seem ordinary, but behave in surprising ways, feel free to suggest them. And if you would like more calm explanations like this, you can subscribe in a low-pressure way whenever it feels useful.